Hello everybody, I'm Edoardo, and today we are going to talk about MediaTek Wi-Fi and how it was possible to completely defeat the firmware encryption. And before starting, well, this talk had been done in collaboration with Daniel Wegemer. So let's introduce the motivation of this talk, because everything started in 2023 when me and Daniel wanted to create a firmware patching framework for exploring the MediaTek Wi-Fi hardware. But, well, we started by exploring old Android smartphone, and then we decided to move on more modern Wi-Fi 5 and Wi-Fi 6 devices. And, well, during our journey, we have encountered a lot of interesting things. For example, an exotic instruction set architecture, firmware encryption, and also hidden firmware secrets inside this Wi-Fi firmware. And in order to solve those challenges, we had to be very creative, and we had also to get our hands dirty. So this talk is for you if you want to understand how everyday devices work, if you are interested in playing with low-level code, and if you want to uncover secrets are coded in remote regions across the firmware. And we needed to do a little bit of presentation about MediaTek because a lot of hardware runs on the MediaTek processor, and well, some security research which were extremely important during the past years were, for example, the complete defeat of the secure boot feature in most Android smartphones. Then also the MediaTek baseband had been completely reverse engineered, and also some exploits were found over the years. And if we want to have a more deeper look about the Wi-Fi chipset used by MediaTek, in the last year, a lot of research had emerged. For example, me and Daniel talked last year in NullCon 2025 about how it was possible to unlock low-level receive mode for MediaTek. And, well, other research were talking about the vulnerabilities present in the driver interface and in some parts of the firmware interface for newer Wi-Fi 7 devices. If we want to have a more broad look in the Wi-Fi ecosystem, think that a lot of devices over the time had been exploited. For example, Broadcom, Intel Wi-Fi, the ESP32, and so on. So before starting, we need to have a solid understanding of what happens when we attach a USB Wi-Fi dongle or when we start our computer with the Wi-Fi card installed. And think that the Wi-Fi card is like a small computer which runs its real-time operating system, which is a small operating system made for embedded purposes. And, well, there is a communication present in between the kernel and the Wi-Fi firmware. So think that we are using a web browser and we need to get some data, some networking data. So the application will open a socket interface and it will communicate with the kernel. The kernel will have the socket handling code, and then it will attach it to the main vendor driver, which is instead used for communicating with the main hardware. And the communication happens through a physical bus, which can be USB or PCI. In case of MediaTek Wi-Fi, most of the devices are PCI. And on the other side, we have the Wi-Fi chipset hardware, which is composed essentially by a ROM and a RAM. The ROM is coded into the hardware and cannot be modified in almost any way. It is also, in general, quite difficult to dump. You cannot access it directly. And then we have the RAM firmware. The RAM firmware essentially is what defines the rulings, the inner workings of a specific hardware. And for example, MediaTek Wi-Fi, it permits to receive and send data. It permits to communicate with the kernel. It permits to start an access point and so on. So now we need to talk about the kernel drivers for MediaTek because we have two main driver families. The first one is called MT76, and it is used in most of the Linux-based devices. So desktop, laptop environments are targeted. And well, it employs a really minimal coding style with a debugging interface under sysfs. And this will be very useful later because we will be able to talk with the hardware through this debugging interface. And well, it is possible also to unlock additional debugging capabilities by applying some kernel patches for this driver, but we won't talk about them for now. And then we have the other two drivers which are used for the embedded environment, so OpenWRT routers and Android smartphones. Just those two drivers are called MT Wi-Fi and Gen4M. And well, compared to MT76, they employ a more verbose code with a lot of comments which are extremely useful for understanding the hardware and the registers used by the firmware. And also, this in general supports the newest devices in most Android phones which aren't implemented in MT76. But for this talk, we will be focusing on MT76 because it is the most widespread driver in the desktop environment. And we need now to look at the firmware for MediaTek. And in general, MediaTek Wi-Fi employs two different firmwares. The first one is called the ROM patch, and it is essentially the first firmware loaded into the ROM memory of the Wi-Fi chipset, and it is taken from the file system. And essentially, it contains some pre-initialization code, some exception handling code, core dump relating function, and additional callbacks pointer, which are used by both the ROM and the RAM firmware for, controlling or adding other commands. And well, the limitation of this ROM patch is that it cannot modify the existing ROM code. And we need also to understand its format because at a certain point, the kernel will parse this firmware and will send some important data back to the ROM, and the ROM will execute this code. So for the ROM patch, we have an header, which is in the top of the file, and this header contains some metadata for indicating each region. A region, if you don't know, is just a chunk of bytes which is sent to the ROM, and in general, it is code or data or something similar, which is executed directly on the Wi-Fi chipset. And a region is described by its offset, which tells the kernel where to seek for finding the start of the region, the length of the region, which is essentially its size in bytes, and then some additional flags, and those are used, for example, from the firmware for indicating if a region is encrypted or not. And this, well, is useful because our talk is about breaking encryption. So now we need to look at the main Wi-Fi firmware, which is by far the most interesting part, and it is loaded after the ROM patch, still from the file system. And it permits the full initialization of the Wi-Fi hardware. This means that it contains everything related to the receive and the transmit path and the communication between the kernel driver and the Wi-Fi MCU. Okay, so compare the firmware structure is a little bit different compared to the ROM patch because because the metadata is placed at the end of the firmware instead of at the top. And instead, if you want to search for the region, you will need to see the first byte. So the first, I think, 900 kilobytes are employed for holding the code and the data that needs to be sent to the ROM, and the last 64 kilobytes are used instead for holding the metadata for defining the region. And each region in the RAM firmware employs a special CRC32, which is used for verifying if a region had been tampered or not. And this CRC32 is placed in the last 4 bytes of each region. So now that we have seen both the kernel drivers and the Wi-Fi firmware, we need to understand what happens when we attach a specific device to our kernel. And well, there is like a booting protocol, and the two main actors which are involved are the kernel itself, the kernel driver, and well, the Wi-Fi ROM code. which for now is still unknown. And well, everything starts from the kernel driver, which requests a lock, and this just says that it will start to upload the ROM patch firmware, the first firmware, and once it will have finished this, will essentially send another command for indicating that this upload process had been terminated, and it will release the semaphore. Now we will enter in the second phase of the firmware loading, and the RAM firmware will be placed inside the memory of the Wi-Fi chipset. This means that for every region, the length of the region data, and the additional region flags will be sent to the ROM, and the ROM will proceed them and will paste the obtained data from the physical bus in the Wi-Fi chipset memory. And once this process is finished, essentially, the ROM will jump at the start of the RAM firmware, and you know, the normal execution of the Wi-Fi firmware starts. So the hardware will start to receive bytes, transmit some bytes, and so on. Now you need to understand that a new protocol is installed on top of the Wi-Fi firmware, so we cannot access anymore the ROM protocol, but instead we will play with a new one, which is implemented in the driver for Linux, Windows, and so on. And for example, let's put that we want to set our card in monitor mode for getting the raw firmware traffic in real time. We need to send a specific command to the RAM firmware, and this command contains many fields, but by far the most important field is called the SID, or the command ID, which is essentially a 32-bit number which indicate a specific callback that needs to be retrieved inside a RAM firmware table stored in the RAM firmware. And well, this callback will be invoked and a function will be called. And when the execution of this function will finish, the result of the function will be sent back to the kernel. So now we need to understand what instruction set architecture runs on the MediaTek Wi-Fi chipset. And in this case, it's called NDS32. So it is a RISC-V inspired architecture created by Andestech, which is a Taiwanese company. And it employs 16 and 32-bit mixed instructions. In general, employs 32 general purpose registers, but the three most important ones are the global pointer, the link pointer, and the stack pointer. So here in the photo you can see the various hardware series implemented by Andestech, but in general MediaTek Wi-Fi will employ the N9 and N10 series. And if we want to get a more deeper understanding of the ISA, we have some resources which are useful. For example, the official manual released by Andestech, the ZCC compiler, the binutils toolchain, for example, the obj dump, which will permit to dump the raw instruction for the firmware. And also we have two plugins for Ghidra and Binja, which will permit to get the compilation of the firmware, and this is useful for the reverse engineering process. So the first thing that we wanted to do was to load the Wi-Fi RAM firmware in Ghidra, but we got some unexpected result. For example, the strings were placed in a wrong offset, and we weren't able to correctly reference them. And also, a lot of instructions were were placed but weren't really implemented. This means that they are like useless. We cannot decode them for now. And for resolving the problems of the strings, we had to study the global pointer register, which is the number 29. And in general, this register permits the efficient access to global and static data by storing a base address to a specific register. And this essentially implements a single instruction access to global data. And the offset that we can target can be arbitrarily big. This means that if we have a strings in memory, we can just sum the offset of the strings plus the global pointer register, and we will be able to reference this. But if we don't have the global pointer address, essentially we won't be able to properly reverse engineering the firmware. And well, regarding the unimplemented instruction, this was due because Andes implemented a custom ISA, which essentially uses an extension called NDS inline function call. And the main purpose of this extension is to reduce the firmware size. And it does this in two different ways. In the first one, it implements two new instructions, if call and if ret. They act like a jump and link primitive. So suppose you have like two functions which uses the same code. Instead of calling each time the instruction, instead you jump to a shared code area which holds the common instruction patterns, you execute them, and then you return back to the if call point, and you execute normally the other remaining code. And then there is the X9 instruction, the one we have seen before, and this essentially permits to reuse the most used 512 32-bit instruction by using an instruction which is only 16-bit long, and the main idea is that it will search inside an array which is placed somewhere in the RAM firmware, and this array contains only 32-bit instructions. So the result will be that the MCU will inspect the array, will retrieve the correct entry, will execute the instruction in the entry, and then will return back to the X9 execution point. Okay, so now we had a problem because Ghidra wasn't supporting this extension. Luckily, last week was added the patch for Ghidra for working even with this special inline function call extension, but I won't talk about it right now. And we, during the time of our research, had to find another way for reverse engineering the RAM firmware, and we decided to work on Radar 2. And thanks to its founder, Pancake, we were able to get the full support for this ISA, including also those unimplemented instructions. And if you can see here, essentially, the compilation works because you can just give the address of the X9 table to Radar 2, and it will resolve every instruction and will replace in memory, and you will be able to get the correct decompilation for the RAM firmware. And well, now we need to focus a little bit on the possible debugging ways for working directly with the hardware, and we need to work on the MT76 driver this time. So essentially, we have some ways. For example, we can obtain the firmware logs. This means that the firmware, when does something, produces some logging data, and this data is sent back to the kernel. It works because you can write a value between 1 and 3 to a special file called the firmware debug. This file under the hood will essentially send a specific command to the Wi-Fi firmware, and as a result, you will be able to get the debugging strings on DMESG. And this is really useful because if you need to know what the firmware is doing at a specific time, you can refer to those strings. Then there is the core dump file. This is another feature, and it is used for diagnostic purposes. So essentially, you send an assert command to the firmware. The firmware will send some crashing data to the dev core dump subsystem, and then it will restart the Wi-Fi chipset. And this core dump file is really interesting because it is a 1 megabyte binary file which is split in two main parts. The first one contains only text, while the second one contains some binary data. We won't talk about it in this talk, but the text part is really interesting because it contains, for example, the last 32 function executed before invoking the crash, the scheduler task status of the firmware, and also the values of the registers. So from these, we can retrieve the real values of for example, global pointer registers, and we can use this value in Ghidra for resolving the strings during the reverse engineering process. And now there is the most important primitive for this driver, which is called the rig index and regval. And this permits essentially to read and write 4 bytes of data directly into the Wi-Fi chipset memory. This is by far the most important primitive because we can inject our code, we can read some code, and so on. And it works because you need to write the address you want to target into the regindex file, and then you can decide if dump the address by reading back the regval file, or overwrite the value pointed at a specific address by writing into the regval file. Okay, so now let's discuss the first real target of today's talk, which is the MediaTek 7921 chipset. It is a Wi-Fi 6 chipset, and you can find it in USB adapters or PCI cards. Essentially, it is used in gaming laptops since 2021. And now the firmware is in plain text, but at the time of this research, it was encrypted with a really simple XOR cipher, and we wanted to reverse engineer it. So the first thing that we wanted to search was in the ROM, because we didn't have the ROM code. It wasn't in the file system, but probably the encrypted firmware was decrypted when during the loading into the ROM. And the first thing that came in our mind was, well, can we try to dump the ROM in some way? Remember the regindex and regval trick? Can we use it? Yes. Essentially, we were able, by iterating the read and write process, to completely dump the first 300 kilobytes of code of the Wi-Fi 6 ROM. And well, we got a binary file. We started to reverse engineer it. And we noticed that this firmware contained really minimal code. It had really few strings. It didn't contain any X9 or if call if write instructions. So we were able to work directly from Ghidra instead of using Radar 2. And well, the ROM uses an unknown real-time operating system called COS, and in our opinions, it is based on ECOS, which is another real-time operating system supplied by Handestech for the NDS32 architecture. And it was possible to get some additional debugging data by reading the source code of the OpenWRT SDK released by MediaTek, which is present on GitHub. And well, we started to reverse engineer the ROM, and the most interesting part is the RAM firmware and the ROM patch download protocol. So now we are seeing the backend of the protocol we have seen before from the point of view of the ROM instead of the kernel. And we still need to retrieve the XOR key. And well, we discovered that this XOR key is processed inside a function called firmware download config, and its main purpose is to retrieve the incoming data from the physical bus and to parse the associated flags with the region which is incoming. And if the flags, for example, suggest that the firmware is encrypted, it will jump to the decryption function. And well, there is like a quite long process for retrieving the XOR key. I want to talk about it. There is like a key selection algorithm, and then there are some function which permits to decrypt each parts of a RAM region. But in general, we were able to retrieve the XOR key, which is 76, 63, and then 20. So if you XOR each byte of this key with 4 bytes of the ROM patch or the RAM firmware, you will be able to completely decrypt the firmware. But now we wanted to patch our firmware and runs back in the Wi-Fi MCU for getting some code execution primitive. And well, we had a big problem because we tried to implement the Nexmon platform for the NDS32 architecture, and when we tried to load our custom Wi-Fi firmware, we got this from the ROM. This means essentially that the ROM is rejecting our RAM firmware, and this, in our opinion, was linked to the CRC32, which was appended in the last 4 bytes of the CRC, of each region. And well, we didn't find even any reverse engineering tool for resolving this CRC32 issue, so we were in troubles. And we need to think about this because we don't know the polynomial and either the initial and final XOR value used for computing this CRC32. And in order to find how this is computed, we had to dive deeper into the ROM. So the answer to our question was the PDA. And what is the PDA? It is a peripheral in the NDS32 Wi-Fi processor. It is a specific DMA hardware which is used to calculate the CRC for each region which is uploaded into the Wi-Fi chipset memory. It isn't documented in the MT76 driver, And you can still find some reference in the empty Wi-Fi and Gem4M drivers instead, which is cool. And well, we cannot either apply some ROM patching techniques for bypassing this control. We need to, in some way, find a bypass way. And we noticed that two registers are involved in the computation of this CRC. The first one is called PDA CRC val, and essentially it is the register which stores the the CRC32 checksum, which had been computed by the PDA for every region. And then we have the PDA.load state, which essentially says if the CRC32 computation was successful or not. So we have found two different ways for bypassing this PDA check. The first one consists of working from the kernel space. So we need to have a modified kernel driver for playing and bypassing the PDA. And the main idea is to use the two register I described before, and for doing this we had to overwrite the last 4 bytes of each region with only zeros, and then load our firmware. And the result will be extremely bad, because we will get only some failures. But if we implement the hardware reading process for reading the PDA CRC val during the boot time in the kernel driver, we will get some interesting values, because you can see that the CRC val initially is set to 0, but during the second iteration is a number, is a 4-byte number, and this number was essentially the computed CRC by the PDA. So the next step is to overwrite the last 4 bytes which were set to 0 into this value which we were able to retrieve. And by doing this, essentially, we were able to forge our own CRC32. And by doing this, we were able also to get our code execution on the Wi-Fi 6 chipset. But now I tried to do something a little bit better, because not everyone can modify a kernel driver for doing this, and there is an additional bypass from this, which is from the user space, so it doesn't use in any way the kernel. And we need to think about the ROM patch, the first firmware which is loaded in the Wi-Fi chipset memory, and the CRC in this ROM patch is never checked. This means that essentially it is completely unsynced, and well, nothing will be verified. The PDA won't touch the ROM patch. So can we do like a firmware layout trick? Can we move the RAM firmware into the ROM patch and then disable in the in the RAM firmware regions metadata the loading flags? This means essentially that at the end we will have a big ROM patch file which will contain also the RAM regions from the Wi-Fi RAM firmware, and on the other side the Wi-Fi RAM firmware will be completely empty. And this worked because at the end, essentially, the ROM patch contains almost the entire code for running on the chipset, and the RAM firmware was empty, it wasn't executed at all, and the PDA never checked both of those files at this point. This was cool because we were able to completely bypass the PDA, but now we wanted also to focus on a more recent hardware, and our choice was the MediaTek 7922, which is a Wi-Fi 6E chipset. It exists only as a PCI card, and it is used in modern laptops since 2024. Essentially, compared to the previous hardware, it unlocks the 6 GHz Wi-Fi bands, and also its bandwidth is doubled, so it is 160 MHz instead of the 80 MHz of the Wi-Fi 6 chipset seen later before. And well, it still employs the NDS32 ISA with the inline function call extension, but this time the firmware, and this means the RAM firmware and the ROM patch, are encrypted in the file system, and they are using the AES-128 zipper, which is far more resistant compared to the XOR zipper we have seen before. And the regindex and the regval tricks isn't working anymore. We cannot read the RAM firmware, or the ROM patch data. And we need to understand how this works, and if it is possible instead to find some code leakage in some ways, and we had to study how the driver communicate over the PCI bus. And essentially in the MT76 source code, every PCI device has an associated table which contains the address translation for reading an offset into the PCI bar address space. This means that we have a complete IO table, and we can try to read every possible address by using the regindex and the regval primitive. So essentially we are brute forcing the entire array for this specific hardware. So I decided to create a tool which permits to dump every specific region and have a big merged L file where every section of the L file corresponds to one section of of the PCI mapping memory. And as a result, 43 segments were dumped, and only one of those contains some valid NDS32 instruction. And this appears to be the last section of the RAM firmware which is loaded into the chipset memory. This means that we can read and write the last 65 kilobyte executable, which are executable in the Wi-Fi RAM firmware. And this is good because now we need to find a way for running our code. We can only read and write it. And well, there is a way because we need to think about a function which is executed in the last firmware region, and this function must be reachable from the kernel space or the user space. And well, we started to think about this, and the obvious idea was to search for some RAM command which was implemented in the last firmware region. Luckily, we don't have the RAM command table because usually stored in the first firmware region, but we have the RAM command table for the previous hardware, and probably it is very similar to this one. So we have compared it, and we have found that there is one command which is quite uncommon. Is called setSPR, and is real use is linked to the layer 1 of the Wi-Fi chipset. But the main idea is that we can, from the kernel space, send a command, and this command is the setSPR function. And if we do this, essentially we will be able to execute some code. So now we will overwrite this callback, which is placed in the last region of the firmware, with our own hand. And by doing this, we will be able to dump some data. So the idea is that we can create like a live patching mechanism where we have a RAM patching code, which is a simple C source code. It is compiled with ZCC, and we get an object file. We extract the executable section in this object file, and through regindex and regval, we patch in the correspondent setSPR command callback. And well, the code essentially is this one, is a simple mem copy, and it reads from the address you are seeing, 0x8000, which is essentially the start of the ROM. And essentially this will copy the ROM data back to another area which can be still read from us. And by doing this, essentially, for every iteration of our setSPR command sent from the kernel space, we are able to dump 1 kilobyte of the ROM. And by doing this at the end, after an entire night used for playing with this, I was able to dump like 300 kilobytes of the ROM, which, you know, wasn't meant to be possible to dump. So we started to analyze this MediaTek 7922 ROM, and it was really similar to the previous hardware. It still didn't implement the X9 and the if call instruction, and we need to find now the AES encryption key for decrypting the ROM patch and the RAM firmware. So essentially, it follows the same path we have seen before for the Wi-Fi 6 ROM. The same function firmware download config is used, and this time the XOR decryption will be completely disabled, and instead we had to explore the AES decryption handling. I won't talk about it because it's a little bit long, but at the end we were able to retrieve the AES key, and I wrote a simple program which, given the two RAM firmware, the two firmwares for MediaTek Wi-Fi, we were able to decrypt the firmwares, and as a result, both the ROM patch and the RAM firmware for the MediaTek 7922 were completely decrypted, and this is important because even today in the Linux repository, in the Linux firmware repository, sorry, on GitHub, you will see that this firmware is encrypted, and by exploiting essentially a bad hardware mapping, we were able to execute our own code in this chipset and to, retrieve the AES encryption key. And now we tried to focus on more recent hardware like the Wi-Fi 7, and in this case is the MediaTek 7925, which is a Wi-Fi 7 PCI card. It is present in high-end laptops and Wi-Fi USB dongles. And well, it employs a new ISA, which is the Andes N45, still Andes, but this time is a pure RISC-V architecture, and it still implements some custom instructions, which are really similar to the X9 instruction we have seen before. But I won't discuss about this because it had been essentially the firmware had been decrypted in the last Black Hat Asia talk about this. So probably there isn't much work on the decryption side for this chipset. The AES key had been retrieved and the firmware is in plain text now. But there was an additional target which wasn't explored, and this is used instead in routers, in really recent routers. Those are, for example, the MediaTek 7990, 7992, and 7996, which are still Wi-Fi 7 PCI cards, which came out in 2024, essentially. And they still use the AES 128 encryption and employs the same ISA of the MT7925. But the OpenWRT SDK for this firmware had been leaked on GitHub. I won't talk about this, but our question was, can we try to dump the ROM and the RAM firmware for bypassing again the firmware encryption? And well, the first thing we tried, even if we were sure it would have failed, was can we use the regindex and the regval tricks for reading writing the memory of the Wi-Fi chipset? And surprisingly, it was possible. So this time, things were much easier, and I was able to dump like the first 5 megabytes of the entire ROM firmware, and the ROM patch address space inside the Wi-Fi MCU. So the entire firmware now is decrypted. And now we need to talk about the future work in this project, because we have still some points to resolve. For example, we want to implement a complete firmware emulation framework which permits to emulate the Wi-Fi 6 and the Wi-Fi 7 MediaTek Wi-Fi devices for additional security testing now that the firmware is decrypted. And also we want to extend the research to the MediaTek Android side, the Dimensity system on chipset, which are used in really expensive Android smartphones. And essentially also another really interesting point is to explore the Bluetooth firmware, because I didn't say this before, but the Wi-Fi chipset has also a USB interface usually, and the Bluetooth interface, sorry, and this Bluetooth firmware was protected by the AES cipher. It was using the same encryption key used by the Wi-Fi firmware. Now it had been decrypted, so it is possible also to read in plaintext the Bluetooth firmware part. And well, now we need to do some final consideration for ending this talk. For example, for the researcher, always search for different drivers because their source code can give extremely important insights for understanding how the hardware is working, the operation involved at the firmware level, and so on. And also GitHub is your best friend, so don't hesitate to search for some leaked SDK, for some leaked firmware, and so on. And for vendors, be aware of every input and output command which is offered by the ROM and the RAM firmware, because by analyzing this interface, you can avoid some firmware decryption attacks and local code execution attacks too. So happy Wi-Fi hacking. If you have any question, let me know. And if you are curious about some of the tools we have been implemented during this project, here our GitHub repository. So thank you very much.